The previous video discussed an interrupt, the math error divide by zero trap that was generated internally to the processor. Let's talk about an interrupt that is generated externally to the processor. Some pins on the PIC24 have hardware on them that allow for change notification interrupts. You can look at the pins and see if they have this designation CN some number that indicates that this particular pin has change notification hardware on it. Change notification hardware will detect any change, either low to high or high to low value in the transition on the pin, and set a flag called the change notification interrupt flag that will generate an interrupt. The change notification interrupt flag is a little bit different from other interrupt flags in the PIC24 in that it can be affected from multiple interrupt sources. Any of the change notification pins can set this flag. Most PIC24 interrupt flags can only be set from one source. In order for this change notification hardware associated with change notification pin to actually affect the change notification flag, the individual change notification interrupt enable bit associated with this particular pin must be a 1 so that this can pass through here and affect this flag. We provide a macro for each change notification pin that can be used to set this bit. Optionally, there is also a change notification pull-up associated with each change notification pin. This pull-up does not have to be enabled in order for the change notification hardware to work. If the change notification flag is set, it will only execute the ISR. The ISR will only be enabled if the change notification interrupt enable bit is a 1 and also the change notification priority is greater than 0. Note that this change notification interrupt enable bit is associated with this particular flag, while this change notification interrupt enable is associated with this particular pin. Let's experiment with using change notification to wake the PIC24 from sleep mode. Previously, we only used a power on or master clear input to wake the PIC24 from sleep, but it turns out that interrupt sources can also wake the PIC24 from sleep mode. What we're going to do is we're going to put a push button switch on RB13, so we're going to configure it as a digital input. We're going to enable the internal pull-up, and we're going to use this macro here, enable RB13 change notification interrupt to enable the change notification hardware on that pin. This delay right here will give a chance for the pull-up to work. This is our interrupt service routine for the change notification interrupt. This is the name you must use for this particular interrupt source. This is the simplest possible ISR in which we're only clearing the interrupt flag associated with this interrupt. It's not doing anything else except clearing that flag. In our main, we're going to call config basic as normal, config the CPU. We're then going to configure our switch, and at this point we want to enable our interrupt. The first thing is always good practice to clear the interrupt flag associated with this interrupt. So we're going to set the change notification flag to a 0. We're going to now set the priority greater than 0. This was an arbitrarily chosen priority. We picked 2. And finally, we're going to enable the interrupt. So here we're going to set this to a 1. At this point, if there's either a low to high or high to low transition on that pin, it's going to generate an interrupt. So at this point, we're going to output a string indicating that we're about to enter sleep mode in our while loop. This particular macro right here is going to wait until all these characters are sent out through the serial port before we actually go to sleep, because we don't want to see a partial message appear. And then at this point, we're going to use this macro to go to sleep. This macro is simply shorthand for our assembly language instruction, power save number 0. So what's going to happen when we execute this program? First of all, we're going to see this string appear, and then the PIC24 is going to go to sleep, and this is going to sit there. When we push the button, we're going to generate a high to low transition on RB13. That's going to generate an interrupt, which wakes the PIC up. It's then going to execute this interrupt service routine, which will clear that flag. Then we'll pick up right here and go back and print this string out again. When I release the push button, then that's going to generate a low to high transition, which will generate yet another interrupt. So the PIC24 will wake up again, clear the flag, and then print the string out. So let's see this program in action. I've programmed my PIC24 with change wakeup.c, powered it on, and now it's printed out this message entering sleep mode. I need to press the button to wake it up. So it's sitting there sleeping. This is the button that I need to press on RB13. I'm going to go in here and I've just pressed it. At that point I generated that high to low transition. I woke up, printed the message, and went back to sleep. When I release it, I will generate the low to high transition, and again it wakes up, prints the message, and goes back to sleep. So the behavior is as expected. One thing that you need to be careful about when using mechanical switch buttons of change notification interrupts is switch bounce. The switch that I'm using is a pretty clean switch and it rarely bounces, but if it bounced, then it would generate an interrupt on each transition. So typically you do not use mechanical switches with edge triggered interrupts such as this. Before we go any further, let's talk about the concept of remappable pins. It turns out that the PIC24 has many internal modules, and these have many inputs and outputs. And somehow we need to get access to these internal inputs and outputs from our external pins. On the particular device we've been using, it only has 28 external pins, of which some are VDD and ground, and so these external pins are very precious resources, and we need some flexible way to map the inputs and outputs of internal modules to these external pins. That's where remappable pins comes in. You can tell if a pin is remappable by looking at the pinout and seeing if it has an RP some number associated with that pin. That means that this pin is remappable and that some internal or external input and output can be mapped to this pin. So this is RP14 remappable pin, this is RP15 remappable pin, and so forth. This particular pin right here, physical pin 9 on this package, is not remappable because it does not have an RP designation. Not all PIC24 family members have remappable pins. You simply have to look at the particular data sheet for that part and see if it offers remappable pins. Each input in an internal module that can be mapped to a remappable pin has an internal special function register field associated with it that if you set it to the number of the remappable pin, it will be mapped to that pin. So for example, if this value right here is set to 13, then this internal input int1 is going to be mapped to the pin RP13. Mapping an output on an internal module to a remappable pin is a somewhat reverse procedure. Each remappable pin has a field associated with it that if you set it to a particular number, it will map it to some particular internal output. For example, this field right here is for RP13. If it's set to a 0, that's the default value. It means it is not mapped to any internal output. However, if we want to map RP13 and bring this output SDO1 for this module to it, what we would do is we would take this field and we would assign it the value 7. These things can be found in the PIC24 datasheet. We have provided some macros that make using these remappable pins easier. These are contained in PIC24_ports.h, and they have the general form of config underscore some internal input or output name to underscore RP, and then followed by some pin number that you want to map this internal input or output to. For example, config U1RX to RP10 will take this input. This is the input for the serial UART module. It takes this internal input and maps it to pin RP10. This is the internal output for the same UART module. This is going to map it to remappable pin RP11. Recall that the change notification interrupt could be configured so that it would generate an interrupt on any transition on the pin, either high to low or low to high. The PIC24 also has 3 other interrupts that can be used for edge triggered interrupts. These are called int2, int1, and int0, and these are more selective in how they work. These can be configured to either be rising edge triggered or falling edge triggered by using an associated special function register bit. This is called the int edge polarity bit. If it's a 1, it's falling edge configuration. If it's 0, then it means the pin is rising edge configuration. On our particular PIC24, it turns out that int1 and int2 must be brought out to remappable pins in order to use them, while int0 is assigned a fixed pin location. We can see that here where int0 is permanently assigned to physical pin 16. So let's take our previous program where we used a change notification interrupt to wake the PIC24 up from sleep mode, and instead let's use int1 to wake it from sleep mode. So in terms of configuration of the switch, we're still going to configure as a RB13 as a digital input. We'll enable the pull up, but now we're not enabling the change notification interrupt. Here is where we're going to configure our int1 to pin RB13, so we're going to map our internal input int1 to our remappable pin RP13, and now we need to configure our int1 interrupt. Here we're going to clear the interrupt flag. We're going to set our interrupt priority to 2. We also need to set the edge polarity bit to either select a falling edge triggered or a rising edge triggered. Here it's going to be negative edge triggered, which means falling edge triggered, by setting this bit to a 1. And finally, we're going to enable our interrupt. In terms of our interrupt service routine, it's going to be like the change notification interrupt service routine, and that the only thing that we're going to do in here is we're going to clear the associated interrupt flag associated with this interrupt, which is int1if. Inside our loop, we're going to do our same thing as before. We're going to print a message out to the screen. We're going to wait until that message is finished transmitting out through the serial port, and then we're going to go to sleep. At this point, the PIC24 is going to be waiting, in this case, for an interrupt to be generated by this int1, which means that it's going to be waiting for a falling edge, which will be generated on a button press. So let's see this in action. I've programmed my PIC24 with this int1 wakeup.c code. So it's printed out this message, and now it's sleeping, waiting for a falling edge on the int1 interrupt. Here I have my push button connected to a remappable pin RP13. So I'm going to go ahead and press it. And when I press it, that generates a falling edge, and so it woke it up, printed out this message, and went back to sleep. Now recall that with the change notification interrupt, when I removed my finger, it also generated another interrupt because the change notification interrupt triggered on any transition of the pin. However, this time when I remove my finger, nothing happens. That's because I generated a rising edge, but the int1 interrupt is only configured to generate interrupt on a falling edge. So let's do that again. I'm going to reach in and I'm going to push the button. I generated a falling edge, so I generate interrupt, woke up, print out this message, went back to sleep. When I remove my finger, it generates a rising edge, but it's not going to generate an interrupt on a rising edge. It's only generating an interrupt on a falling edge.